Hi there fellow friends, welcome back to the channel. Today's video will be slightly different from the ones that I posted before. Today I want to show you how to create parametric designs in Fusion360 and most importantly how to organize your project and get started. So if you're a beginner when it comes to 3D printing, to Fusion360, to parametric designs, you've come to the right place, as today I'm going to show you exactly how to get started and how to create your first parametric design in Fusion360. I've been doing 3D design for mechanical assemblies for quite some time already. And for most of them, which are a bit more intricate and complicated, I'm always using parametric design. Why, you may ask? Because it's much simpler to iterate and it offers you much more flexibility when it comes to modifying the parts after you created them, after you put them into your assembly. And after all, it only comes down to modifying a few parameters and your 3D design can be reiterated and can be changed, can be easily updated. So without further ado, let's dive right in. Today we'll have 4 topics to cover. The first one being how to set up Fusion360 for parametric design. The second one would be how to add parameters to Fusion360 sketches and solid assemblies. Third one would be how to add dependent parameters, so parameters that would depend on other values from the other parameters or from simple constants. Lastly, the fourth point would be adding parameters for tolerances, which is especially important for 3D printing and if you work with collaborators. Parametric design is a design approach where geometric elements and relationships are defined by parameters. That means that these parameters can describe lengths, can describe angles, can describe number of repetitions or some more complex formulas where you say, for instance, the number of shelves in a cabinet. This can also be a parameter. And the main reason why you would want to use parametric design is basically flexibility, efficiency, and most importantly, after all, the speed of iteration. So you can just update some parameters, send it right to 3D printer again and check it if it works better. Now, you first need to open up Fusion360 and we'll start with the basics. We should think about some design constraints from this point in time. What you want to create, you should think about it before starting Fusion360. For instance, in my case, I would like to create a 3D part that resembles a triangle that would be part of a larger assembly. This assembly will have interconnecting faces and should be parametric, mostly because I want it to be easily modifiable on the fly. So I can change some parameters, then export as STL, add some features, then export again as STL, and so on and so forth. These triangles would have a side length, the length of the side of the triangle, which should be a parameter. So let's create exactly that. I'll go into modify, then change parameters, and then I have this table right here where the parameters for my project will be visible. If you click on this plus, you can enter a name, a unit, expression, value, or comments. Let's say triangle side, and it should be represented in units of millimeters, and I'll use 57.735 millimeters. You might ask what's with this value, and you can also add a comment below it, and I will say value for triangle height equal 50, and that's basically the reason why I choose this value, and you will see in a minute. Let's go with the triangle height, and it will be also represented in millimeter, and this time we can use some geometric formulas to calculate the height of the triangles. So you have the triangle side, which is a normal parameter with no dependency. It's basically defined, expressed as a constant, but you can also add parameters which are defined by formulas. So for instance, triangle height for a triangle which have equal sides on all 3 sides is defined by the length of the side multiplied by the square root of 3 divided by 2. So let's type exactly that. I will use the triangle side multiplied by sqrt, which is a function that you can find in Fusion360. I will leave a link in the comment with all the functions that can be added to the expressions. so that you can give it a read and get familiar with how they work. So you can basically call them here, and you can put inside basically 3, which is the square root of 3, and then divide by 2. And as you can see here, the result is exactly 50, and that's why I chose the specific 57.735 value for the triangle side. With that in mind, the height of the triangle would be 50, which is a round number, and if you have a assembly like I will have, with many triangles one next to each other, you will have in the end an assembly with a uniform value in terms of length for width and length. Alright, so we had set 2 parameters already. That's our starting point. Next, we can set the thickness for which we will extrude this triangle sketch. So let's set triangle thickness again in millimeters. Let's set it to 8, and we should be good to go for now. Let's start creating the triangle. I will create a random triangle with no particular sizes, and now we can define it. Let's go with this one. This is not defined correctly, so this side should be triangle side. Hit enter. This one should be also triangle side. Hit enter. And last but not least should be again the same triangle side. And with that in place, you have your triangle with all 3 sides equal. Let's clean it up a bit, and I will show you another thing. Basically, the distance from the apex of it to the bottom is exactly 50. I would not create or over define the sketch, it's just to show you how the value goes into place. Now let's extrude it by hitting E or using the press pull function, and set the thickness to thickness. And by setting the thickness like this, you can see we created a 3D triangle with the required thickness. There is one thing I would add as well, which is a chamfer for each side. We can add parameters also here, so let's do exactly that. Go to modify parameters and add a few more, and let's say chamfer or triangle chamfer, and set its expression to a value that would be dependent on the side. Why we are doing that? Mostly because we want to have a uniform scalability in case we use a triangle of double the sides or the triple the sides. Also, the chamfer would be proportional. So if we have a 57.735 multiplied by 2 side of the triangle, then we want to have double the chamfer as well. So let's set exactly that. We'll use the triangle side and we'll divide that by 8. I think that's a good number for starting. 7.217, it's pretty fine. And I would also add a triangle face chamfer, which should be half of the thickness. So it will look better when you print it. It will have a nice tapered top, and it will look much better. So let's define exactly that. Should be thickness divided by 2, which will result in 4. And with that out of the way, we can select the faces that we want to chamfer, for instance these ones, and we can select here the triangle chamfer. And as you can see, it's already chamfered to the required dimension. And last but not least, add the chamfer for the face, and also type in here face chamfer. And as you can see, it's looking quite a bit better now. Of course, the fun part about this is that you can modify the parameters while you do your thing in the 3D design space. So let's make this a bit bigger, and basically let's set the thickness to 10 millimeters. And as you can see, the chamfer is also updating in real time. So let's go with 50 millimeters. And I think that's a bit too much. Let's go for 20. I think 20 is much better. It's not looking pretty, but it works. So let's go back to 8 millimeters, and you can see that it's half of the thickness. Also, the chamfer for the side can be updated in real time. I can, for instance, go with 5, which will create a much larger chamfer, but I can also do 10, which will be a smaller one. This one only depends on how you like your parts to look, but play around with them, see what works for you. Now, this is just a triangle with some chamfers, and that's basically it. So let's turn this into a functional part. Let's make a holder for a toothbrush. I will bring the sketch into this design and we can make a functional part out of this. By using the timeline feature that is built in Fusion, you can go right click, edit sketch, and now you can easily add more features to this sketch. So let's start with a circle. I will place it randomly. I need it to be 22.5 millimeters, but you might wonder what's with this value. Shouldn't it be a parameter as well? And in that case, you are very right. This should be also a parameter because it defines the outer diameter of the toothbrush, and you might get this wrong on the first try. So you can easily modify it by having it set as a parameter. We don't have it yet, so let's create it. Toothbrush support should be fine, 22.5 millimeters. And here we go, we have it defined here. Let's also name it properly here, toothbrush support. Now, there's a reason why I chose a triangle with equal sides, mainly because the median of each apex goes into a point, which is also the center of the triangle. But how you define that? So mathematically, it's defined as 1/3 of the triangle height. So we've created the triangle height already. We have the value, which was the side multiplied by square root of 3 divided by 2. In this case, we can use that one to describe where this circle should be in our sketch. So let's define a distance between the center of the circle and the bottom or the base of the triangle. And let's define this as height multiplied by 1/3. And also, for safety, let's define this also with the reference to the other sides of the triangle. So in case we ever want to have the triangle larger, then this circle will stay perfectly centered, but only if the sides are equal, which will be because we define them all as a parameter. So that would be height multiplied by 1/3. And also regarding this side, it will be driven by the other two. So we have it centered. Now, because we can also use it later, let's enable this sketch and use this one to create our pull or our extrude, our cut. Let's set the start to this object, which is the face of the part, and set the thickness. But now you may ask, let's create also a thickness parameter, right? So let's do exactly that. Go to change parameters, again bring it into focus and have toothbrush cut thickness. And let's go for 7 millimeters. And with that done, I will do again the object extrude and then here type minus toothbrush cut thickness. And as you can probably already see, it's already cut into our part. I would add one more thing, and that would be a chamfer with two sides this time to better support the toothbrush when you put it in place. So let's do exactly that. I will go to modify, change parameters, and have now set two chamfers. So we'd say toothbrush chamfer to center, and I would set that to 1.5 millimeters. And I would also add a toothbrush chamfer to ceiling or seal. Let's set it like this, of 4 millimeters. That's just the naming I came up with. You can use any names you want, so that's up to you. So let's create that chamfer. I will set two distance, and this one, the first one, would be the ceiling, and I will check and use the one to ceiling. And as you can see, it slightly created something there, and the other one would be to center, and that would look like this. And by hitting enter, you can see we created a slight taper inside our cut, onto which the toothbrush will rest properly. I would add just actually I think that could be also one distance and could be the toothbrush to center because it's smaller, 1.5. No, it's a bit too much, so just divide it by 2 and should be quite good. Okay, that's looking much better. So with that in place, there's one more feature I would add to this, which is actually the pin that holds the toothbrush in place. So we have the cutout, the outer body of the toothbrush would rely on this place, and there's a pin that goes in the middle that would hold the toothbrush in place. I will just grab the sketch from the other design and get ready to implement it here. So now let's create a sketch on this face, which is the inner diameter of the inner face of the circle that we cut. And as you can see, I also placed here a sketch. You can use the caliper to measure this sketch, you can use anything. This can vary from one toothbrush to the other, so we'll just start with it as given. Alright, so we got the design into place. Let's move it somewhere near to where it should be, and also create a point that would be in the middle here. And let's start this defining the parameter. Let's start with the height first. So let's go for the triangle height multiplied by 1/3, and that should be it. And also define this side here as triangle height multiplied by 1/3. And as you can see, it's already in the center as it should be, and you can also over define it by setting this parameter right here, but it's a driven, so we won't bother with it. And at this point in time, if you want to ever change the sizes of your base triangle, let's say for instance make it 65 millimeters, you can see that this will stay perfectly in the center as you wish. So let's set it back to the required dimension, and that should be it. So now I would create a parameter that describes the length of this pin, how much it's extruded outside. So let's go for toothbrush pin length, and I will set that to 12 millimeters, and let's extrude it. Toothbrush pin length, and as you can see, it's already set to 12 from the parameter. There's only one thing left here, just some fillets to make this look a bit better, and that shouldn't be a parameter from my perspective, as it's just, yeah, that should be it. As you can see, that's basically a functioning part with a design that can be modified with ease. So for instance, if you want to change the triangle side, or you want to have a different value for the height, you can calculate it offline and then go into Fusion360 and update your values so that you have the correct size. And everything would be updated in regards to your setup. So let's change, for instance, the thickness to 10 millimeters. It's just updated and working properly. There should be some interference with design here with this feature, but should be also good to go. So you can play with it a bit and design as you wish. The toothbrush support, for instance, you can have it larger, like 4.6, and you can see it's updated in real time. You can have it also to 24, let's say. Let's show this sketch first, and I'll use this point to create an axis. I did an axis perpendicular to a face, and with that in place, I will show you how such assemblies should look or will look, I'll select this body, then create a circular pattern, and I created 6 equal triangles like my initial one. Of course, you can also create assemblies that are defined by parameters, but let's make a custom fixing point for this set of 6 triangles. Imagine you would have these 6 fixed on a wall, and they are designed in such a way, if you look from the side, with this angle that goes 45 degrees and goes to the half of the thickness, so you can create a clamp that would fit right into that place and clamp your assembly to the wall, to the table, to anything you need. So let's do exactly that. Starting again with a sketch, select the required plane, and now I would create a circle that would be roughly 5 mm in diameter. Let's say I would be fixing everything with metric 5 screws, 5 mm in diameter. And I would also need circle based on which I will define a hexagon that will go into this place. So let's set it to 12.5. If you wonder from where this 12.5 come, I will do a quick sketch and show you. This should be as normal or construction for now, and let's just extend from this point. Let's zoom or select maybe this one. So let's zoom, click on a point, go to this one, then to this one. I will have them roughly the size. So these are 7.218 in length, which is the chamfer size that we set in our parameters. If you go here, the triangle chamfer, it's 7.217, and if you calculate the height of this 7.217, you'll get exactly the radius of this circle. So let's use actually the parameters to do that. I would need the diameter of this circle would be circle for hexagon. I will just type it hex for short. And I would need the triangle chamfer, to which I would multiply the square root of 3, and then I will divide it by 2. And as you can see, it goes 6.25. This would be used for my circle, but it shouldn't be 6.25 because that's the radius, and I need the diameter, and I will just remove the divided by 2 at the end. And with that in place, I can just delete these references I created for explanation, and you can see this can be diameter circle for hex. And this should be another parameter that I will create now, which should be circle for screw, and that should be 5 mm. Now creating a polygon, circumscribed polygon to be exact, I would set it exactly to this value of 12.5, and as you can see, it fits perfectly into place. Finish the sketch and select it. I can extrude it to another parameter, which would be thickness divided by 2, and I will show you in a moment why. And I'll create a new body out of it. And as you can see, it's all the way to the intersection between the other triangles, and let's extrude it a bit more for another thickness divided by 2. But this time I will do a taper angle of 45 degrees, just so it clamps all the pieces as you want. I'll hide all the bodies so I can join it with the original one. And last but not least, I will show the sketch, select the inner diameter and extrude cut it also. And what remains now to do is to create just a simple parameter that would define the chamfer for my mounting place. So ideally you should have half of the diameter of the bolt or of the screw as chamfer. So let's go with 2.5. I'll go to modify, change parameters, add a new parameter, circle, screw, chamfer, and that would be circle for screw divided by 2. And in this way, if I ever change the screw size from M5 to M4 or to M6, then the chamfer would be automatically adjusted. And then go to chamfer and say chamfer, circle, screw, chamfer, hit enter, and you're good to go. Hide the sketch, and that should be it. So that's how you create a pretty simple assembly with parametric design. But there's one more thing I would like to show you, which is actually how to include tolerances directly into this design. So tolerances are quite important for your projects, especially when it comes to 3D printing. Having a parameter that defines your tolerance level for each connection between parts is very important, as you might collaborate with friends, with colleagues, with other fellows from the 3D printing community, and you want their prints to look quite good. And if you ever share your Fusion360 parametric file, then they should be able to update the tolerance that you set so that it will work properly on their machines as well. So let's do exactly that. I'll create a new parameter which is called tolerance, and that should be 0.1 for my machine. That works perfect. And let's do a few changes to our part. As you can see, this fixing part here is basically glued to the other parts, which will never work in 3D printing. Let's add some tolerances for that. First, I also need a tolerance for the inside diameter of the screw. So we will add this tolerance depending on how we want it to be, either positive or negative tolerance. Let's start with the inner diameter of this screw. I have circle for screw, which is 5 millimeters, or I would need a hole that's slightly larger that will accommodate the screw quite easily. So let's go for 5.1, which is actually 5 millimeter plus tolerance. And that's going to be 5.1. Let's hide some of these bodies so it's easier for you to see. As you can see right here, these faces are very close to each other. The distance between them is basically 0 millimeters. I would need to have circle for hex slightly smaller so that there will be a gap right there. And if I do that and hit enter and go outside of here, I should be able to see some differences, which I'm not seeing. And you might ask why. If we go back to the sketch, you'll see that there's some definitions which are missing because we haven't ever put them yet. So let's use the timeline function in Fusion360 and edit this sketch. And as you can see, this dimension is correct, which is 12.4, but there is a distance between our circle and our limits for the hex. So let's do another thing. Set a distance between these 2 points as the circle for hex. And that would mean it will also be 12.4. And I don't actually need to over-define it because it's already defined on this dimension, and that should be good to go. And now if I hit finish sketch, through the power of parametric designing, you can see that there's a small 0.1 millimeter gap between our parts. That can also be visible on this part here. So if I go on the bottom side, you can see this air gap. Of course, you might have your 3D printer slightly less calibrated, and in that case you can just add a bit more tolerance. So let's go for 0.25, and our design is already updated in real time. So that should be it. That's basically how you create a parametric design and how you set it up. And if you do everything properly, at the end, if you just change the dimension of the triangle side, for instance, say you want to have it 75 millimeters, you just hit enter and everything will be recalculated by Fusion and you'll have your parts ready to be used. And that's also the case here. As you can see, it's quite important to know how to do parametric design, especially when it comes to 3D printing, when the iterative process is quite slow and you want to have everything set up properly from the beginning. Now, let's do a summary of what we've learned today. We've set up Fusion360 for parametric design, we defined some constraints from the beginning. Those constraints would be saved as parameters and then used in the design. Then we created dependable parameters, which are the parameters that have been created depending on previously defined parameters, which were constants. Then we used a special parameter for tolerance with, of course, its importance for manufacturability. And then we created an assembly and tested everything together and saw how they interact with each other. With that in mind, you should be good to go to start doing parametric designs for your small projects. It's just an introduction, but it should be quite well structured for now. If you are curious what's this design about and where does the triangles thing come from, then I would recommend you subscribe and turn on the notifications, since this would be part of a project that I've been working for some time, and it will be open source, fully parametric, and will provide a bit more value than you expect for your organizing needs back home. If you have any questions or got stuck on any steps that I showed you so far, you can just drop a comment down in the comment section below and I will make sure to come and help you as soon as possible. If you like this kind of videos more than the project ones, just let me know. I might create a few with more complex topics. Maybe I can create a full crash course on Fusion360. You tell me. And with that being said, until next time, stay creative and have a nice one.